Hello everyone, welcome in the video lecture of integrated circuits. In today's lecture, we are going to discuss monostable multivibrator using 555 timer IC. So let us start with the introduction of 555 timer IC. As we already know that we can realize the multivibrators with the help of operational amplifier also, and with the help of timer IC, that is 555 timer IC, we can realize the same multivibrator. What is 555 timer IC? The 555 timer IC was introduced in the year 1970 by Signetic Corporation, and it is named as NE/SE555 timer. So what is the reason we used to call it as 555 timer IC? First of all, why it is called as timer IC? Because this IC is dedicatedly designed to design the timing based applications. With the help of this particular IC, we can produce very accurate and highly stable time delays or oscillations. So that is why it is called as timer IC. Why it is called as 555? Because in its internal circuit diagram, we use 3 resistors of value 5 kilo ohm in series. That is why it is named as 555. Okay, so what is 555 timer IC? First of all, because it is used to design the timing based applications, that is why it is called timer IC. And why it is called 555? Because inside its internal circuitry, we are using 3 resistors, 3 fixed resistors of 5 kilo ohm in series. Now, this 555 timer IC is available in dual inline package. It is 8-pin IC. Dual inline package means equal amount of pins are available on both the sides, 4 pin on each side. At pin number 1, we have the provision of ground, which was not available in 741 op-amp IC. At pin number 2, it is called as trigger pin. As we know that we can use this IC in monostable mode and as well as in astable mode. So in monostable mode, we are required to apply an external triggering pulse. So to connect the external input, we can use pin number 2, which is called as trigger pin. Pin number 3 is the output pin, from which we can observe our output. Pin number 4 is the reset pin. What is pin number 4? Reset pin. What is reset pin? If this IC is operating in any of the mode, monostable mode, astable mode, or it is operating in any other condition, and we want to reset or we want to disable the operation of the IC, we can do it by applying a negative pulse on pin number 4. So pin number 4 is used to reset the operation of IC. That is why it is called as reset pin, that we can do by applying a negative pulse on pin number 4. Pin number 5 is the control voltage. We can externally control the output of comparator. Inside its internal circuitry, we will have 2 comparators, upper comparator and lower comparator. So in the upper comparator, this pin number 5 is connected, and if we want to control the threshold voltage externally, we can apply by connecting a potentiometer at pin number 5. So that is why it is called as control voltage. Pin number 6 is the threshold pin, that is again connected to the non-inverting terminal of the upper comparator and will be used to compare the non-inverting and inverting terminal of upper comparator voltages. Pin number 7 is the discharge pin. What is discharge pin? This pin number 7 is internally connected to the collector of a transistor. If binary 0 will appear on the base of transistor, the transistor will operate in cutoff mode, and most of the time a capacitor is also connected to the transistor, and the capacitor will start charging when the transistor is operating in cutoff mode. When binary 1 will appear on the base of transistor, the transistor will act in saturation mode or it will act like short circuit. When the transistor is operating in short circuit mode, then the capacitor will start discharging. So basically on pin number 7, what operation is happening, that is the charging or discharging of the capacitor. So that is why this pin number 7 is called as discharge pin or the discharge terminal. At pin number 8, we used to connect the biasing, that is plus VCC, that may vary from plus 5 volt to plus 18 volt. It is a single supply IC and we can bias this particular IC at pin number 8. So this is the pin configuration of 555 timer IC. Now we can use this 555 timer IC in monostable mode as well as in stable mode. In today's lecture, we are going to discuss the operation of this timer IC in monostable mode. So from the lecture of monostable multivibrator with the help of op-amp, we know what is the meaning of monostable multivibrator. Monostable multivibrator, or basically what is multivibrator? Multivibrator is a kind of non-linear oscillator with the help of which we can generate pulse signals, the square waveform, triangular waveform and so on. With the help of monostable multivibrator, we can generate a pulse signal of a particular duration when we will apply an external triggering pulse to the circuit. Why it is called monostable? Because in this particular circuit we will have one stable state and one quasi-stable state. This monostable multivibrator we know is also called as one-shot multivibrator, because corresponding to one external trigger pulse we will get one output pulse or one unstable state or one quasi-stable state at the output of the circuit. Okay. So the same monostable multivibrator operation that we have realized with the help of operational amplifier IC 741, we can realize with the help of this 555 timer IC. What will be the difference between the both? Because this IC is specifically designed to produce very accurate and highly stable time delays or oscillations. So here we will get more accuracy in comparison of op-amp IC. Fine. Otherwise, we can develop this particular circuit with the help of op-amp as well as with the help of 555 timer IC. The basic difference, we will get more accuracy if we will realize this circuit with the help of 555 timer IC. So what is monostable multivibrator? Where we will have only one stable state and one quasi-stable state, and it is also called as one-shot multivibrator. If we want to change the state, that is the stable state of the circuit, to the unstable state, that is called as quasi-stable state, then we have to apply an external triggering pulse. That external triggering pulse will be applied on pin number 2 of this particular IC. So when the triggering is applied, it produces a pulse at the output of fixed duration, and after that the circuit will again come back to its stable operation or the stable state. So let us discuss the operation of this monostable multivibrator, how we can achieve this operation of monostable multivibrator with the help of 555 timer IC. Here we have the internal block diagram of 555 timer IC in monostable mode. So what we have done here, how we can achieve the monostable multivibrator operation by connecting an external resistor and capacitor to the 555 timer IC, we can realize the operation of monostable multivibrator with the help of 555 timer IC. Let us first quickly discuss what are the main components, internal components of this 555 timer IC. Here we will have two comparators called as upper comparator and lower comparator. UC stands for upper comparator and LC stands for lower comparator. We know what is the operation of comparator. The comparator is used to compare the voltages available at its inverting and non-inverting terminal. For example, if the potential of non-inverting terminal is higher than the potential of inverting terminal, then what will be the output? The output will be equals to plus Vset, that is equals to plus VCC. When the potential of inverting terminal will be higher than the potential of non-inverting terminal, then what will be the output? That is called as minus V saturation. and which is equivalent to minus of VCC. So, if plus Vset is occurring at the output of comparator, that will be considered as logic 1, and if minus Vset is occurring at the output of comparator, we will consider that is equivalent to logic 0. Okay. So, here we have two comparators that will compare the voltages available at its inverting and non-inverting terminal. Then we will have one SR flip flop, that is set and reset flip flop. How this set and reset flip flop work, let me discuss in brief. So, what is the truth table of SR flip flop? First, if we will have 0 0 input combination, then what will be the output state? We have two output states, Q and Q bar, complement to each other. So, if our input combination is 0 and 0, the output, there will be no change in the output state, that is called as hold or the previous state. Whatever is the state of the flip flop just before this combination, the flip flop will maintain that particular state, whether it was set state or reset state. If R is equals to 0 and S is equals to 1, then what will be the output? Q will be 1 and Q bar will be 0. This is called set state of the flip flop. Okay. If R is 1 and S is 0, then Q will become 0 and Q bar will become 1. This is called reset state of the flip flop. For an instance, if both the inputs are 1, then both the outputs tends to be similar, which is not possible because both are complement to each other. So, this is called invalid state, and we generally avoid this particular input combination for SR flip flop. Fine. So, we have to keep in mind, when both the input combinations are 0 0, then there will be no change in the state. If R0 S1, this is the set state, and if R1 and S0, this is the reset state. So, in our internal block diagram of 555 timer IC, we will have one SR flip flop. The input to this SR will come from the output of comparator. The output of comparator will be either plus Vset or minus Vset, depending upon the voltage at which terminal is higher. Plus Vset will be considered as logic 1, minus Vset will be considered as logic 0. So, this will make S and R to be 0 0, 0 1 or 1 0, corresponding to which we will get the output Q and Q bar. Fine. Further, this Q bar is connected to an inverter, and we are taking our output from the output of inverter. This Q bar is further connected to the base of a transistor. This transistor is called as discharge transistor. This transistor is called as discharge transistor. So, what will be the output of this flip flop? Either 0 or 1. Fine. So, if 0 is the output of this flip flop, that is the, if Q bar is 0, then 0 will appear at the base of this transistor. If 0 is appearing at the base of transistor, the transistor will behave like open circuit. What is logic 0? Basically, it is like the low voltage. So, if low voltage is appearing at the base of a NPN transistor, this circuit will be in cutoff mode and will behave like open circuit. When this transistor will be open circuit, then further this is connected to this particular point, this path will be broken. Fine. If Q bar is 1, then 1 will appear at the base of transistor. If 1 is appearing at the base of transistor, what it does mean? It means high voltage. For this one, it will be in saturation mode and it will act like short circuit. So, when it is in short circuit operation, this path will be maintained. Fine. So, we have two comparators, one flip flop and one discharge transistor. Other than this, we are having 3 resistors of fixed 5 kilo ohm values, 5 kilo ohm, 5 kilo ohm and 5 kilo ohm. Because of these 3 5 kilo ohm resistors, we used to call this IC as 555 timer IC. Then at pin number 1 we have ground. Here we have our pin number 1. Pin number 2 is the trigger pin. It is connected to the inverting terminal of lower comparator. Here we have pin number 2. Then pin number 3 is the output pin. Here we will have our pin number 3. Pin number 4 is the reset pin. The reset pin will be connected to this Q with the help of a transistor, let's say V reference, and when we will apply a negative pulse at the base of this transistor, this IC will be reset. So here we will have our pin number 4. Then pin number 5 is the control voltage, which is generally connected to this particular point, which is the inverting terminal of upper comparator. Then pin number 6, that is the threshold voltage. It is the non-inverting terminal of upper comparator. It is this point. Pin number 7 is the discharge terminal, which is internally connected to the collector of discharge transistor. It is this point. Then pin number 8 is the power supply. That is this point. Fine. So now let us discuss the operation of this circuit in monostable mode. How we will get the output pulse or the unstable state when we will apply triggering pulse to this particular circuit. So let us now discuss the working of monostable multivibrator using 555 timer IC. So to switch the output state, we have to trigger the circuit, and the triggering will be applied at pin number 2. So let us consider that initially, when we have not applied any triggering pulse, the magnitude of this triggering pulse, the positive magnitude of this triggering pulse Vt is much greater than 1/3 of Vcc. Okay, and its magnitude in negative direction is lesser than 1/3 of Vcc. So the moment we have not applied any triggering pulse, the potential at inverting terminal is much higher than the potential at non-inverting terminal. So the output of lower comparator will be minus Vset, that is equivalent to logic 0. Fine. On the upper comparator side, when we have just turned on the circuit, there is no voltage across the capacitor, and the voltage across the capacitor we can consider as 0 volt. This is the potential of non-inverting terminal of upper comparator, 0 volt, and inverting terminal is at 2/3 of Vcc. So the output of upper comparator will also be at logic 0, that is minus V saturation. So when both the inputs of the flip-flop are at 0, 0, there will be no change in the output state. Output is in stable mode, that is Q bar is equals to 1 and Q is equals to 0. When Q bar is equals to 1, we are taking output by inverting the Q bar's output, that is equals to 0. So for this, if I want to draw the waveform, what I am getting initially, what will be the output of monostable circuit? It is low state, which is the stable state, and I have not applied any triggering pulse. So till the moment negative triggering pulse is not applied, the circuit will be in its stable state, and it will keep on maintaining its stable state. Now the moment I will apply the triggering pulse, so what will happen when I will apply a triggering pulse Vt, whose magnitude in negative direction is much lesser than the 1/3 of Vcc. So when the triggering pulse is applied, the potential at inverting terminal will become lesser than the potential of non-inverting terminal. So the output of lower comparator now will switch from logic 0 to logic 1. Fine. There is no change in the upper comparator input terminals. So R becomes 0, S becomes 1. For S is equals to 1, the flip-flop will acquire set condition or the set state. For that, Q will become 1 and Q bar will become 0. And the output will change its state from 0 to 1, which is the quasi-stable state. So the moment triggering pulse will come, the output will switch from low to high state. Fine. Now let us observe what will happen with the upper comparator. Q bar now becomes 0. This 0 is going to the base of this transistor. When 0 is occurring at the base of transistor, the transistor will operate in cutoff mode and it will act like open circuit. So when the transistor is open circuit, this path will be broken from power supply to the ground. When this path between the power supply and ground will be broken, then it will start taking this path to the ground through capacitor. Now the capacitor will start charging towards 2/3 of VCC. So what will happen when the capacitor will start charging towards 1/3 of VCC? Initially, the voltage across the capacitor was 0 volt. Now it is gradually charging towards the 2/3 of VCC. Meanwhile, let us observe what is the output of upper and lower comparator. Capacitor is charging towards 2/3 of VCC, but it is still lesser than 2/3 of VCC. So the output of upper comparator will remain at logic 0. Below, at the lower comparator, the moment I have applied the trigger pulse, the output of lower comparator was changed from 0 to 1. The duration of this triggering pulse was very short. So the moment I have applied, it will change the output of lower comparator and it will change the state of the flip-flop. Then, as the duration of the triggering pulse is very low, after a certain duration, the output of this lower comparator will again become logic 0. Okay, because again the positive part of this pulse is much greater than the 1/3 of VCC and the output of lower comparator will become 0. At the upper comparator we are getting 0, at the lower comparator we are getting 0. Before this 0 0, what was the state of the flip-flop? It was in set condition. So the output of the monostable circuit will be in quasi-stable state. Now the capacitor will keep on charging towards 2/3 of VCC. The moment the charging across the capacitor VC will become greater than 2/3 of VCC. The moment the potential at this non-inverting terminal becomes slightly greater than 2/3 of VCC, the output of upper comparator will switch from logic 0 to logic 1. Okay. So the moment the capacitor voltage will cross 2/3 of VCC, the output of upper comparator will become logic 1. The output of lower comparator is still at logic 0. R1S0, the flip-flop will acquire reset condition. Reset condition means Q bar will become 1 and Q will become 0. When Q bar will become 1, the output will become 0. That is its stable state. So the moment the charging across the capacitor is greater than 2/3 of VCC, the output state of the circuit will again switch from unstable state to stable state. That is from high state to low state. Now let us check when Q bar is 1, then the logic 1 will appear at the base of transistor. Now this transistor for logic 1 will behave like short circuit and again the path between the power supply and the ground will be established. Now this capacitor will start discharging. The moment capacitor voltage will become lesser than 2/3 of VCC, the output of upper comparator will again become 0. So for 0 0, before this 0 0, what was the last state of the flip-flop? That is the reset state. So it will keep on maintaining its reset state, that is its stable state, until I will apply next triggering pulse. So in this manner, when I have applied, till the moment I have not applied any triggering pulse, I am getting the stable state from the monostable circuit, that is the low output. And the moment I have applied the triggering pulse, it will switch its state from stable to quasi-stable state for a particular time duration capital T, and after that it will again acquire its stable state. So in this way we will get a we will be able to generate a pulse at the output when we will apply an external triggering pulse. Okay, so we can design this monostable circuit for the fixed duration of quasi-stable state, that we can decide for how much of duration it will be in its quasi-stable state. That can be done by this, that we can calculate with the help of this simple derivation. We will start from the voltage across the capacitor, because this change in state of the flip-flop is depending upon the charging and discharging of the capacitor. Voltage across the capacitor is given by VCC1 minus exponential of minus T by RC. So what we want to calculate? We want to calculate change in the state when T is equals to capital T. For how much of duration this capital T will be maintained? Till the capacitor voltage will not reach 2/3 of VCC. So at T is equals to capital T, when VC becomes 2/3 of VCC, we are required to calculate the time duration. So at T is equals to capital T, VC will be equals to 2/3 of VCC. When I put this value in this equation, I will get this value. 2/3 of VCC is equals to VCC 1 minus exponential of minus T by RC. We want to calculate the value of this T, time duration of the unstable state. So we will solve this equation for this small t. To eliminate the exponential, we will take natural log both sides. On solving the natural log of 1/3, we will get time period of the quasi-stable state, or the external pulse that we are getting is 1.098 times of RC, or is equivalent to 1.1 times of RC. So we can design this monostable circuit for this desired pulse width duration by selecting proper value of the external resistor and capacitor that we have used at these two positions. Okay. So now how we can give the pin diagram of monostable circuit? We can draw this pin diagram like, at pin number 1 we have the provision of ground. At pin number 5, if it is not in use, we will bypass this pin number 5 with a capacitor of value 0.01 microfarad. From pin number 3, we used to take the output. From pin number 4 and 8, at pin number 8, we used to connect the power supply VCC in the range plus 5 volt to plus 18 volt. Pin number 4 is the reset pin. When it is not in use, we will short this pin with the power supply pin. At pin number 2, we used to apply the triggering pulse. At pin number 7 and 6, these two pins are shorted, and further they are connected to an external resistor and a capacitor, C and R. These are the two external components with the help of which we can design this 555 timer IC in monostable mode for a desired pulse duration, that is equals to 1.1 times of R. So this will be the pin configuration of monostable circuit, 555 timer IC pin configuration. This monostable circuit can be used for variety of applications, like we can use this monostable circuit as a frequency divider. We can use this monostable circuit for the generation of pulse with modulated signal, pulse position modulated signal in communication. We can use it as a missing pulse detector, and also this circuit can be used as a timer in relays. Okay, so these are some applications of our monostable multivibrator with the help of 555 timer ICs. So in this video lecture, we have discussed the working of 555 timer IC in monostable mode, where we have discussed how we can change the stable state of monostable circuit by applying an external triggering pulse, and how we can generate a pulse of desired duration. What will be the relationship between the pulse duration in unstable state and the resistor and capacitor that we have connected externally? What should be the pin configuration of monostable circuit in using 555 timer IC, and what are the application of this monostable multivibrator circuits? So this is all about this video lecture. Thank you everyone.